Right now, every measurement your civilization has ever made of the universe's expansion rate might be wrong, not because the instruments are broken, not because the math is flawed, but because of where we happen to be standing. We are inside a bubble of space roughly 2 billion light-years across where matter is measurably thinner than it should be. The galaxies are fewer, the density is lower, and the gravitational landscape has been quietly distorting our view of the cosmos for as long as we have been looking. This is not a speculative idea waiting to be tested. In 2013, 3 astronomers mapped the positions of 35,000 galaxies in every direction from Earth and found the same thing each time they looked: a persistent, consistent 20% shortfall of matter. Not a gap in one patch of sky, not a quirk of a single telescope. A uniform deficit in all directions, stretching outward for over 1 billion light-years, with our galaxy sitting somewhere inside it. That structure has a name, the KBC Void. It is named after the 3 astronomers who identified it: Brent Tully, Amy Barger, and Lennox Cowie. Most people have never heard of it, but the KBC Void may be one of the most consequential discoveries in modern cosmology because it connects directly to a crisis in physics that has been building for years, a crisis about whether the universe itself is even the age we think it is. When Cowie, Barger, and Keenan began their galaxy survey, they were not hunting for anomalies. They wanted a more accurate picture of the large-scale structure around us, a better catalogue of what exists, where it sits, and how its density compares to what cosmological models predict. What they found was a systematic shortfall. Across every direction they pointed, the actual galaxy count within roughly 1 billion light-years was about 20% lower than theoretical models said it should be. That deficit was not clumped in one region. It was spread uniformly in all directions, forming an enormous sphere of underdensity centered somewhere close to our position. They checked their data against multiple independent galaxy surveys. They approached the sky from different angles. The answer remained consistent. They had found an underdense bubble so vast that it dwarfs every previously identified void on record. This placed Earth, its galaxy group, and the entire supercluster containing all of those, within one of the most extreme low-density environments ever observed. At first glance, a void might seem like a minor feature. Space is full of gaps between galaxy filaments. Voids are expected, but the KBC void is not the ordinary emptiness between clusters. Its scale, its depth, and its apparent statistical rarity are what make it explosive. And as scientists began working through the implications, they found it connects to a problem that was already keeping cosmologists up at night: the Hubble tension. The Hubble constant is one of the most fundamental numbers in cosmology. It tells us how fast the universe is expanding, specifically, how many kilometers per second a galaxy recedes from us for every megaparsec of distance between us. 1 megaparsec is about 3.26 million light-years. There are 2 main methods for measuring this number, and they give different answers. The first method works backward from the cosmic microwave background, the faint glow of thermal radiation left over from when the universe was about 380,000 years old. By feeding the detailed temperature patterns of this ancient light into cosmological models, scientists can calculate what the expansion rate must have been in the early universe, and from there, what it should be today. This method consistently returns a value of around 67 kilometers per second per megaparsec. The second method builds what astronomers call a distance ladder using nearby objects with known intrinsic brightness, type Ia supernovae and Cepheid variable stars. Cepheid variable stars pulsate at a rate that correlates precisely with their luminosity, which means if you can see one pulsing, you can calculate exactly how bright it truly is. Compare that intrinsic brightness to how bright it appears in your telescope, and you have its distance. Type Ia supernovae burn with such consistent peak brightness that they serve as cosmic measuring sticks across billions of light-years. Combining these distance measurements with the redshift of their host galaxies gives the local expansion rate directly. This method consistently returns about 73 kilometers per second per megaparsec. That gap, 67 versus 73, represents a 9% discrepancy. Both measurements are precise enough that random error cannot explain it. Both have been independently verified by multiple research teams using different instruments and different techniques. The discrepancy has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance it is just random variation. This is the Hubble tension, and it is one of the most actively debated problems in modern physics. Here is where the KBC void enters the picture with a possible answer. When the local Hubble constant is measured using supernovae, those supernovae are sitting inside the same void we inhabit. The void's low matter density changes the local gravitational landscape in a very specific way. All of the mass that is missing from the void, that 20% deficit spread across 2 billion light-years, does not simply cease to exist. It is concentrated in the denser filaments and walls surrounding the void. That exterior mass pulls on galaxies inside the void, tugging them outward. Those galaxies are not just receding because space is expanding. They are also being accelerated outward by the gravitational imbalance created by the void's geometry. There is more mass outside pulling outward than there is mass at center pulling inward, so galaxies inside the void gain an additional outward velocity component on top of the expansion. When astronomers measure the recession speed of these galaxies and convert it to an expansion rate, they get a number that is inflated above the true global average. The void is giving galaxies within it an extra outward kick that mimics faster expansion. Calculations show that a void of the KBC's scale, roughly 1 billion light-years in radius with a 20% density deficit, can produce precisely the boost needed to explain the observed discrepancy between the two Hubble constant measurements. This does not mean scientists made errors. It means the measurement is accurate, but the location from which it was made introduces a systematic bias. We are not measuring the universe's expansion rate. We are measuring the expansion rate as seen from inside a gravitational anomaly that amplifies the apparent value. It is like trying to measure average air pressure while standing inside a weather balloon. To understand what it means to be inside the KBC void, it helps to have a clear picture of our position in the cosmic hierarchy. The Milky Way is one of about 80 galaxies that form the local group, a gravitationally bound collection spanning a few million light-years that includes the Andromeda Galaxy, the Magellanic Clouds, and dozens of smaller dwarf galaxies. The local group is itself part of a far larger structure called the Laniakea supercluster, identified in 2014 by mapping the velocity flows of galaxies across our region of the universe. Laniakea contains roughly 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian and translates roughly to immeasurable heaven. The structure is defined not by proximity alone, but by gravitational flow patterns. All of the galaxies within Laniakea are flowing toward a common gravitational center called the Great Attractor, a massive concentration of matter about 250 million light-years away that exerts an enormous gravitational pull on everything in our local region. The Milky Way sits on the outer edge of Laniakea, and we are gravitationally bound to it. Our peculiar velocity, the motion of our galaxy beyond what simple cosmic expansion would predict, is partly directed toward the Great Attractor. We are falling toward it slowly, even as the expansion of space stretches the distance between us. Here is what is remarkable about this. Even Laniakea, with its 100,000 galaxies spanning over 500 million light-years, sits entirely inside the KBC void. The KBC void is so vast that a structure the scale of Laniakea barely registers as a perturbation within it. Our position within the void is not at its center. Measurements suggest the Milky Way is roughly 200 to 400 million light-years from the true center of the void. But the void extends about 1 billion light-years in every direction from that center. We are well inside it, surrounded by this low-density environment in all directions. Beyond the void's edge lies a shell of higher density structure, filaments and clusters where the density rises back toward the cosmic average. When astronomers look outward from Earth through their telescopes, they see this shell as a concentration of galaxy clusters at a specific distance range. It is the void's outer wall. Beyond it, the universe returns to something closer to normal density. In addition to the large KBC void, we are also adjacent to a smaller but distinct underdensity called the local void, which spans about 200 million light-years. Our galaxy is actively flowing away from the local void at around 260 kilometers per second as part of a broader outflow pattern called the local sheet, a flattened arrangement of galaxies that includes the Milky Way and Andromeda. Adding all of these gravitational effects together, the pull toward the Great Attractor, the outflow from the local void, the gravitational influence of the nearby Virgo cluster, and the future merger trajectory with Andromeda, gives the Milky Way a total peculiar velocity of roughly 627 kilometers per second relative to the cosmic microwave background rest frame. That figure corresponds to a temperature dipole observed in the microwave background itself, and it is consistent with exactly what you would expect from a galaxy sitting inside a large underdense region. We are not stationary, we are moving fast, and the void is a significant reason why. Voids are the dominant structural feature of the universe by volume. Roughly 90% of the total volume of space is void. The filaments, walls, and clusters that we tend to focus on occupy only the remaining 10% of the volume, but they contain most of the mass. This distribution emerged from the earliest moments of cosmic history. In the first fraction of a second after the Big Bang, during a period called cosmic inflation, the universe expanded exponentially. Quantum fluctuations at subatomic scales were stretched to cosmic scales. These fluctuations imprinted tiny variations in density across the early universe, some regions denser by perhaps 1 part in 100,000, others slightly less dense. Those differences seem negligible, but gravity amplifies them over time. Denser regions attracted more matter from their surroundings, becoming denser still. Less dense regions lost matter to their neighbors, growing emptier. Over hundreds of millions of years, this process built the architecture we observe today, a cosmic web of filaments and sheets surrounding vast hollow regions. The voids are not truly empty. They contain dark matter, just at much lower concentrations than average, roughly 15% of the cosmic average density. They contain dark energy, which is uniformly distributed throughout space and therefore present in voids at the same density as everywhere else. They contain occasional wisps of hydrogen gas and the rare isolated galaxy, but they lack the gravity to build new structure. Without sufficient mass, gravity cannot pull matter into clusters or form new filaments. The void stays a void. This is where dark energy becomes important. In dense regions, gravity and dark energy compete. Gravity pulls matter together while dark energy pushes space apart. The two forces partially cancel, and the expansion of dense regions is slower than the cosmic average. Inside voids, this competition does not exist. With so little matter, gravity contributes almost nothing. Dark energy dominates, and voids expand faster than the rest of the universe. This creates a self-amplifying dynamic. The faster a void expands, the emptier it becomes, which reduces gravitational resistance to further expansion. Voids grow like bubbles, pushing outward and compressing the surrounding filaments into denser, thinner walls. The effect has a measurable signature. Astronomers have observed that galaxies near void edges move outward faster than expansion alone would predict. The velocity surplus matches what you would expect from the gravitational pull of the denser matter, outside the void acting on the interior. The physics is geometric. Think of the void as a low-density valley surrounded by high-density ridges. In gravitational terms, there is more mass pulling galaxies toward the ridges than toward the center. The net effect is an outward flow from the void's interior. This same physics applies to the KBC Void and produces our galaxy's unusual speed. The surplus motion is detectable. It is consistent with the void's measured properties, and it directly affects every nearby measurement of cosmic expansion. The existence of the KBC Void would be interesting regardless of its size, but what makes it scientifically explosive is that it should not exist, or at least should be extraordinarily rare. The standard cosmological model, known as lambda cold dark matter, or LCDM, has been remarkably successful at explaining the large-scale structure of the universe. It predicts how structures grow from the initial density fluctuations left by inflation, accounts for the observed temperature patterns in the cosmic microwave background, explains the abundance of light elements produced in the Big Bang, and correctly describes the general appearance of the cosmic web. One of its key predictions is a statistical distribution of void sizes. Small voids, tens of millions of light-years across, should be common because they form from common small-scale fluctuations. Medium voids should be less common. Extremely large, deep voids should be very rare because they require very large initial underdensities that are statistically improbable given the smoothness of the early universe. When researchers run computer simulations of structure formation using standard parameters and look for voids comparable to the KBC Void, roughly 2 billion light-years across with a 20% density deficit, they find almost none. Some analyses estimate the probability of such a void occurring in the observable universe at roughly 1 in 1,000. Others have calculated that the KBC void represents a 10 sigma deviation from expected density, meaning you would need to survey trillions of universe-sized volumes before expecting to find a single such structure by chance. To put that in context, a 5 sigma result is already considered practically impossible in physics and is the standard threshold for claiming a discovery. A 10 sigma result is incomprehensibly more improbable, yet we live in one. This creates an immediate logical tension. Either the standard cosmological model is missing something important about how large structures form, or we happen to occupy an extraordinarily unusual position in the universe. Neither answer is satisfying from a scientific standpoint. Both are deeply uncomfortable in different ways. Critics of the standard model point to the KBC void, along with other large-scale anomalies like the Shapley supercluster and the Sloan Great Wall, as evidence that structure formation in the real universe is more vigorous than the model predicts. Something may be missing from LCDM that would allow larger, deeper voids and richer clusters to form without requiring rare initial conditions. Defenders of the standard model note that the cosmos is large enough that even improbable events can occur somewhere, and that nearly every other prediction of LCDM has been confirmed with high precision. They argue that abandoning a successful theoretical framework based on one anomalous structure is premature, especially when measurement uncertainties about the void's exact depth and extent remain. Different observational techniques have produced density deficits ranging from about 10% to 20%. If the true deficit is closer to the lower end, the statistical rarity becomes less severe. One of the oldest alternative gravity theories is modified Newtonian dynamics, or MOND, originally proposed to explain why galaxies rotate faster at their outer edges than standard gravity predicts without dark matter. MOND adjusts the force law at low accelerations. When applied to cosmological structure formation, MOND produces more vigorous clustering, denser clusters, and deeper voids compared to standard Newtonian gravity combined with cold dark matter. Computer simulations using MOND gravity naturally generate voids with the scale and depth of the KBC void without requiring unusual initial conditions. The statistical improbability disappears. However, MOND faces serious difficulties beyond galaxy rotation curves. It struggles to explain gravitational lensing observations in galaxy clusters, where the observed bending of light requires more mass than MOND's enhancement of visible matter can supply. It also does not reproduce the fine-scale temperature patterns in the cosmic microwave background as accurately as the standard model. A broader class of modified gravity theories adjust the behavior of gravity on cosmological scales without changing its predictions on smaller, well-tested scales. Some introduce additional fields or higher dimensional effects that effectively make gravity stronger in low-density environments like voids. If gravity is enhanced in voids, those regions would drain their matter faster and reach greater depths, making large supervoids more probable. Testing whether gravity deviates from general relativity in void environments is now a major goal of observational cosmology. Another approach focuses not on modifying gravity, but on the initial conditions left by inflation. Standard inflationary models predict a nearly scale-invariant spectrum of density fluctuations, meaning all scales contribute approximately equally to the initial density contrast. Some modifications to inflation can produce extra power on large scales, meaning bigger fluctuations at the scale of supervoids. If the inflationary spectrum had slightly more power at scales corresponding to billions of light-years, large voids would form more easily, and the KBC void's existence would be less improbable. Underlying all of these debates is a foundational assumption in modern physics called the cosmological principle. It states that the universe is homogeneous, the same everywhere, and isotropic, the same in all directions, when averaged over sufficiently large scales. No location is special. No direction is preferred. This principle is not just a philosophical preference. It is a mathematical convenience that makes the equations of general relativity tractable for describing the universe as a whole. Without it, cosmological models become vastly more complicated. With it, a few simple parameters describe the entire history and structure of the cosmos. The cosmological principle has been remarkably productive. It underpins the standard Big Bang model, the predictions of the cosmic microwave background, and the standard model of cosmology. But the KBC Void creates friction with this principle. A structure 2 billion light-years across with a 20% density deviation is a significant inhomogeneity. It is large enough to represent a meaningful fraction of the observable universe's volume, and we are near its center. The uncomfortable implication is that our location may not be typical. Science has made a long historical trend of removing Earth from any special position. Earth is not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of the universe. The cosmological principle is the final step in that progression. Not only are we not at the center, but there is no center because all positions are equivalent. The KBC Void, if it is as extreme as the most detailed measurements suggest, implies that Earth does occupy an unusual position inside one of the largest known underdensities in the observable universe. That does not put us at the center of anything, but it does mean our location is statistically far from ordinary. If the cosmological principle does not hold at the scale of the KBC Void, then measurements made from our location, including every local measurement of the Hubble constant, are systematically influenced by our unusual vantage point. We may be trying to infer universal properties from a position that does not sample the universe fairly. Cosmic voids have an unusual scientific value that extends beyond their challenge to standard models. They are the best natural laboratories in the universe for studying dark energy. Dark energy was discovered in 1998 through observations of distant type Ia supernovae. Astronomers expected to find that the expansion of the universe was slowing down, that gravity would be pulling matter back together and decelerating the expansion over time. Instead, the supernovae appeared fainter than expected, indicating they were farther away than a decelerating universe would place them. The expansion was accelerating. Some energy component was pushing space apart. Dark energy now accounts for about 68% of the total energy content of the universe, according to the standard model. Unlike matter or radiation, it does not dilute as the universe expands. Its density appears to remain constant even as space itself grows. This gives it an ever-increasing share of the cosmic energy budget and a growing influence on cosmic dynamics. The simplest interpretation is that dark energy is a cosmological constant, an intrinsic energy density of empty space that is constant throughout time and uniform across all locations. Albert Einstein introduced this concept in his field equations, though he later considered it an error. But this is not the only possibility. Dark energy could be a dynamic field that varies in strength with time or space. If it was weaker in the past and stronger now, expansion would have accelerated differently over cosmic history. If it varies across locations, it would affect structure formation differently in different environments. In dense regions, gravity and dark energy compete. The expansion in and around galaxy clusters is slowed by the gravitational pull of all that mass. Disentangling the dark energy signal from the gravitational noise is difficult. In voids, matter is scarce and gravity is negligible. Dark energy operates almost unimpeded. The expansion of voids is essentially a direct measurement of dark energy's repulsive influence. By measuring how fast voids expand, how quickly their edges push outward, and comparing that to predictions based on different dark energy models, scientists can constrain dark energy's properties with unprecedented precision. If dark energy is a cosmological constant, voids should expand at a rate that matches the standard model precisely. If dark energy evolves or varies, the expansion rates will deviate. The KBC Void, being both the largest known nearby supervoid and the one we can study in most detail due to its proximity, is particularly valuable for these measurements. The low-density environment of a void does not just affect large-scale cosmology. It shapes the formation and evolution of the galaxies that develop within it. Galaxies inside voids grow up in relative isolation. Unlike galaxies in dense clusters, which frequently interact with neighbors, colliding, merging, stripping gas from each other, and feeding material into each other's central black holes, void galaxies evolve with minimal external interference. This environmental difference produces distinctive characteristics. Void galaxies tend to be smaller and less massive than their counterparts in filaments and clusters. Many qualify as dwarf galaxies, barely large enough to hold onto their gas against the outward pressure generated by star formation. Without the mass to anchor their gas and the gravitational encounters to fuel growth, they remain relatively modest structures. Mergers are a key driver of galaxy evolution in dense environments. When two galaxies collide and combine, the gravitational disruption compresses gas clouds and triggers intense bursts of star formation. Merger-driven star formation is responsible for many of the most massive and luminous galaxies we observe in rich clusters. It also feeds material into supermassive black holes, making them grow and sometimes activating quasars, enormously luminous episodes of black hole accretion that can outshine entire galaxies. In voids, this process is largely absent. Galaxies evolve on their own internal dynamics. Their star formation rates are generally lower, and their growth is gradual. They retain disk structures and spiral arms that would be disrupted by mergers in denser environments. There is a surprising twist, however. While most void galaxies are quiescent, a disproportionate fraction of them undergo brief, intense episodes of star formation called starbursts. This seems paradoxical until you consider the gas reservoir. In dense environments, galaxies continuously lose gas through interactions with neighbors. Tidal forces strip material from their outer disks. The hot, diffuse gas filling galaxy clusters can also ram pressure strip gas from infalling galaxies. Void galaxies avoid these processes. They retain their neutral hydrogen for longer, building up large reservoirs of unprocessed gas. When something internal eventually triggers star formation, perhaps a minor internal gravitational instability, there is an abundance of fuel available. The result is a brief but intense starburst that consumes a large fraction of the gas reservoir before the galaxy settles back into relative inactivity. The chemical composition of void galaxies also differs. Stars create heavy elements through nuclear fusion and disperse them into the galaxy's gas when they die in supernovae. Later generations of stars form from this enriched gas, and the galaxy's overall metallicity, the abundance of elements heavier than helium, gradually increases over time. This process is slower in void galaxies because they form stars at lower rates. Void galaxies tend to have lower metallicities than galaxies in dense regions. Now consider what the KBC Void does to one of cosmology's most fundamental parameters, the age of the universe. The current best estimate for the universe's age is 13.8 billion years. This comes from detailed modeling of the cosmic microwave background combined with the standard cosmological parameters, the matter density, the dark energy density, and the expansion rate derived from early universe measurements. If the local Hubble constant measurement of 73 kilometers per second per megaparsec reflects the true global expansion rate rather than a void-inflated local value, the universe has been expanding faster throughout its entire history. A faster expansion rate means the universe reached its current size in less time. Calculations show this would imply a universe about 12.7 billion years old, roughly 8% younger than the current estimate. This creates a concrete problem. The oldest stars in globular clusters, spherical collections of hundreds of thousands of stars that formed together in the early universe, appear to be about 13 billion years old based on stellar evolution theory. The dating method is straightforward in principle. Stars of different masses burn through their nuclear fuel at different rates. By observing which stars in a cluster have just barely reached the end of their main sequence lives, astronomers can estimate when all the stars in that cluster formed. You cannot have stars that formed before the universe existed. A 12.7 billion year old universe with 13 billion year old stars is self-contradictory. White dwarf cooling times provide an independent age constraint that does not depend on stellar evolution models. White dwarfs, the remnant cores of dead stars, cool gradually and predictably as they radiate stored heat into space. The coolest white dwarfs we have found have been cooling for approximately 12 to 13 billion years. This independently confirms a universe older than 12.7 billion years. The cleanest resolution comes from accepting the void explanation for the local Hubble constant excess. If the 73 km per second measurement is inflated by our position inside the KBC Void, then it does not represent the universe's global expansion rate. The cosmic microwave background measurement of 67 kilometers per second per megaparsec applies to the early universe and to the global average, and the derived age of 13.8 billion years remains valid. The apparent discrepancy between local and early universe measurements is not evidence that the universe is younger. It is evidence that our local neighborhood is unusual. This resolution preserves the age of the universe and removes the contradiction with stellar ages, but it requires accepting that every precision measurement made locally over the last few decades has been systematically biased by our position inside an extraordinarily large cosmic void. The questions raised by the KBC Void will not remain unanswered for long. A new generation of astronomical surveys is already underway or in preparation, designed with the precision to resolve the key uncertainties. The Euclid Space Telescope, launched in 2023 and beginning full science operations in 2024, will map the positions and shapes of billions of galaxies across a large fraction of the sky and out to distances of many billions of light years. Its primary scientific goals include measuring the expansion history of the universe and the growth rate of large-scale structure. These measurements will directly test whether the dark energy driving cosmic acceleration behaves like a cosmological constant or like a dynamic field that evolves. Euclid will also discover and catalog thousands of voids at different distances and sizes, providing the statistical sample needed to determine how rare supervoids like the KBC Void truly are. The Vera Rubin Observatory in Chile, when it reaches full operational capacity, will conduct the Legacy Survey of Space and Time, a decade-long photometric survey that will observe approximately 20 billion galaxies over the southern sky. This survey will map the three-dimensional distribution of matter to greater depth and completeness than any previous instrument, providing the most detailed picture of the cosmic web yet assembled. It will also discover supernovae at a rate of roughly 10,000 per year, improving the local Hubble constant measurement with unprecedented statistical power. If the KBC Void's influence on these measurements is real, the pattern should become unmistakable in Vera Rubin's data. The Dark Energy Spectroscopic Instrument, known as DESI, is already operating and mapping galaxy spectra at a rate of millions per year. Its goal is to measure the Hubble constant, the growth of structure, and the equation of state of dark energy through baryon acoustic oscillation measurements using the characteristic spacing of galaxy clustering as a cosmic ruler. DESI results are expected to significantly tighten constraints on all of these parameters and to map the velocity field around the KBC Void in unprecedented detail. The Square Kilometre Array, currently under construction in South Africa and Australia, will survey neutral hydrogen across the universe at radio wavelengths. Neutral hydrogen is the raw material of star formation and traces the distribution of matter in ways optical surveys cannot. The SCAR will map void interiors, characterize void galaxies across cosmic time, and measure how gas content evolves in low-density environments. It will test the predictions of standard and modified gravity theories about how matter flows in and around voids. An entirely new observational window on the universe's expansion rate has opened in recent years: gravitational wave astronomy. Since the LIGO detector's first detection of gravitational waves from merging black holes in 2015, and especially since the 2017 detection of a neutron star merger accompanied by a gamma-ray burst and optical counterpart, gravitational wave observations have offered a new method for measuring the Hubble constant. Neutron star mergers are what physicists call standard sirens. Like type Ia supernovae serving as standard candles, neutron star mergers can be used as distance indicators. The amplitude of the gravitational wave signal depends on the intrinsic properties of the merger and on the distance to the source. By analyzing the gravitational waveform, physicists can extract the distance to the merger without any electromagnetic observations. If that distance is combined with a measurement of the host galaxy's redshift, the Hubble constant can be calculated directly. The first such measurement from the neutron star merger GW170817 returned a Hubble constant of approximately 70 kilometers per second per megaparsec, right between the early universe estimate of 67 and the local ladder estimate of 73, with an uncertainty of about 14%. As more events accumulate, the uncertainty will decrease and gravitational wave cosmology will independently determine which end of the tension range is more correct. Crucially, that merger occurred in a galaxy about 130 million light-years away, squarely within the KBC Void. If the void is inflating local distance measurements, the gravitational wave measurement would also be affected, though in a different way than the supernova distance ladder. As detectors improve, the event rate will increase to dozens or hundreds of detections per year. With a large sample of events at various distances, the dependence of the apparent Hubble constant on distance will be measurable. The prediction from the void hypothesis is that events within the void should return a systematically higher Hubble constant than events at distances beyond the void's edge. This prediction is directly testable once enough events have been detected across the full range of relevant distances. The future Einstein telescope in Europe and the Cosmic Explorer in the United States will be enormously more sensitive than current detectors, detecting neutron star mergers out to distances of many billions of light-years. These instruments will produce catalogues of thousands of standard sirens, spanning both the interior of the KBC Void and the more typical density regions beyond it. The resulting Hubble constant measurements as a function of distance will provide one of the most direct tests of whether the void is responsible for the local Hubble tension or whether some other explanation is needed. Consider the dynamic history of the void itself. It has not always been as empty as it is today. In the early universe, the cosmic web was just beginning to assemble. The first stars ignited in dense knots of hydrogen about 100 to 200 million years after the Big Bang. The first galaxies assembled over the following hundreds of millions of years. The filaments connecting these galaxies and the voids separating them were smaller and less pronounced. The structure was there, but density contrasts between voids and filaments were smaller than today. Over the past 13 billion years, gravity has been working continuously. Dense regions have drawn in more and more matter, growing richer. Voids have emptied progressively, losing matter to the surrounding filaments. The cosmic web has become increasingly pronounced over time, with higher density contrasts between voids and clusters. Dark energy adds a complicating factor. For the first several billion years of cosmic history, matter dominated the energy budget and gravity determined how structures evolved. But as the universe expanded, the density of matter thinned out while the density of dark energy remained approximately constant. About 5 billion years ago, dark energy became the dominant component. Since then, the accelerating expansion it drives has been competing with gravity. In this dark energy-dominated phase, the growth of structure has slowed. Voids are still expanding, but the rate of new cluster formation has decreased. In the far future, this process will continue. The Milky Way and Andromeda will collide and merge in roughly 4 billion years, forming a new combined galaxy. This merged structure will be the dominant object in the local group, but the local group itself will become increasingly isolated as the accelerating expansion pushes other nearby groups beyond our cosmic horizon over tens of billions of years. As cosmic expansion accelerates, galaxies beyond a certain distance will recede faster than light can bridge the gap. They will effectively disappear from the observable universe. The local group will find itself in an expanding void of its own, cosmically isolated, even if not locally lonely. Over trillions of years, star formation will gradually cease as gas is consumed or expelled from galaxies. The night sky will darken as the stellar population ages. The last stars will exhaust their nuclear fuel. Galaxies will consist of stellar remnants, white dwarfs gradually cooling toward invisibility, neutron stars, and black holes. Eventually, gravitational interactions between these remnants will scatter most of them out of galaxies entirely, leaving isolated objects drifting through an expanding void. Through a quantum mechanical process described by Stephen Hawking, black holes slowly evaporate by radiating energy over incomprehensibly long timescales. A stellar mass black hole would take roughly 10 to the 67th power years to evaporate. Supermassive black holes would take far longer. But eventually even they would disappear. What remains is a diffuse, cold, expanding sea of particles and radiation. The voids that are a notable feature of today's universe will become everything. The filaments and clusters we see as the defining structures of the cosmic web are a transient phase, impressive on human timescales, but ephemeral in the context of cosmic time. The universe's long-term destiny, given what we understand about dark energy, is progressive emptiness. The void we inhabit is not an anomaly of the present moment. It is a preview of the ultimate state of the cosmos. If the content of what you are learning here is genuinely fascinating to you, consider subscribing. The questions being asked in modern cosmology are among the most profound that science has ever attempted to answer, and there is much more to explore. Several key questions about the KBC Void remain unresolved and represent the frontier of current research. The most immediate is the exact depth and extent of the void. Measurements from different surveys and different teams have returned density deficits, ranging from roughly 10% to 20%. The statistical significance of the void and how seriously it challenges standard cosmology depends heavily on which end of that range is correct. Better galaxy surveys with greater depth and sky coverage will pin down these numbers. Until they do, arguments about the void's statistical rarity rest on somewhat uncertain ground. The causal connection between the void and the Hubble tension remains under scrutiny. The void hypothesis predicts specific patterns in how the locally measured Hubble constant should vary with distance, decreasing as measurements extend to larger scales and exit the void's sphere of influence. Recent observations show hints of this trend, but the data are not yet decisive. More precise measurements of the expansion rate at different distance scales will test whether the void is the dominant explanation for the tension or merely a contributing factor. The question of whether the void challenges or violates the cosmological principle also remains open. Homogeneity is expected to hold at scales of several hundred megaparsecs and above. The KBC Void spans roughly 600 megaparsecs, right at the boundary. Whether the principle is violated depends on both the precision of the void's measured properties and on theoretical questions about exactly what scale homogeneity is supposed to manifest. The deeper unsettling possibility is that our location inside the KBC Void might introduce biases we have not yet thought to look for. Every measurement of cosmic expansion, every inference about dark energy, every statistical analysis of large-scale structure made from within the void carries the imprint of our unusual position. Quantifying those imprints, distinguishing what we observe because it is universally true from what we observe because we are standing inside a particular hole in the cosmos, is one of the central challenges of observational cosmology over the coming decade. The resolution, when it comes, will likely not arrive in a single dramatic announcement. More likely, new surveys will gradually refine the void's density profile. The Hubble tension will be pinned down with higher precision at multiple distance scales. The velocity field within and around the void will be mapped with new clarity, and models will be adjusted to accommodate the accumulated evidence. The adjustment may be minor. Perhaps standard cosmology underestimates the frequency of large voids by a factor of 2 or 3 without requiring new physics. Or it may be significant. Perhaps the void requires modified gravity or altered inflationary physics, demanding a genuine revision of the theoretical framework. In either case, the universe will remain strange and the work will continue. The KBC Void is not an anomaly in the dismissive sense of something that can be wished away. It is a feature of the cosmos, a real, measurable, enormous region of below-average density that surrounds our galaxy in every direction and extends for 1 billion light-years. Its reality is not in question. Its full implications are. We live in a remarkable time for cosmology. The instruments coming online in this decade are genuinely capable of answering questions that have been unresolvable for the past generation of astronomers. The data that Euclid, Daisy, Vera Rubin and their companion experiments will return over the next 10 years will be transformative. The maps they produce will settle the statistical question of the void's rarity. The expansion rate measurements will resolve or deepen the Hubble tension. The dark energy constraints will narrow the range of possible physical explanations. Our galaxy is inside a bubble of space 2 billion light-years across where matter is measurably scarce. We know this with confidence. What we do not yet know is what that tells us about the universe beyond the bubble, whether the standard framework describes that universe correctly, whether gravity and dark energy behave as we expect on scales we cannot yet map precisely, and whether our current measurements are telling us something about the cosmos or something about the unusual corner of it we happen to inhabit. Those are the open questions, they will be answered. The void, for all its emptiness, turns out to be one of the most information-rich environments in the observable universe, not despite its emptiness, but because of it. There is a subtlety to the void's influence that most discussions skip past, and it is worth spending time on. The void does not just affect the speed at which galaxies appear to move away from us. It affects the geometry of the space through which light travels before it reaches our telescopes. Light traveling through a region of below-average density takes a slightly different path than light traveling through average density space. The gravitational lensing effect is reduced. The integrated Sachs-Wolf effect, a subtle imprint left on the cosmic microwave background as photons travel through evolving gravitational potential wells, is altered. The integrated Sachs-Wolf effect works like this. When a photon from the cosmic microwave background enters a region of higher than average density, it falls into a gravitational well, gaining energy. If the universe were matter-dominated and not expanding, it would lose exactly that energy climbing back out the other side. The total energy change would be zero. But in a dark energy-dominated, accelerating universe, the gravitational potential of density structures weakens over time. The potential well the photon climbed out of is shallower than the one it fell into. The photon exits with a net energy gain. This creates a measurable hot spot in the cosmic microwave background aligned with large-scale structures. The reverse happens with voids. A photon passing through a large void loses energy going in because it climbs out of a shallow, low-density region. But in an accelerating universe, the potential well deepens slightly as the void expands. The photon exits with less energy than it entered with. This creates a cold spot in the microwave background aligned with large voids. This prediction has been observationally confirmed for several large void structures and provides one of the most direct pieces of evidence that dark energy is causing the universe to accelerate. The KBC Void, being the largest known supervoid in our vicinity, should produce a measurable integrated Sachs-Wolf signal. Detecting and mapping this signal is a goal of current and upcoming microwave background experiments. If the signal matches the predicted magnitude from the void's density profile, it confirms that the void is a genuine physical feature and not a measurement artifact. If the signal is stronger or weaker than predicted, it constrains dark energy properties in a way that complements the expansion rate measurements. The Sunyaev-Zeldovich effect provides another independent confirmation of the void's existence. When cosmic microwave background photons pass through a galaxy cluster, they interact with the hot gas filling the cluster, gaining energy through a process called inverse Compton scattering. This shifts the photons to slightly higher energies, creating a characteristic spectral distortion in the microwave background. By looking for this signature across the sky, astronomers can build catalogs of galaxy clusters purely from their microwave background imprint. These catalogs are largely independent of optical galaxy surveys because they trace the cluster gas rather than the stars. When the distribution of clusters detected through the Sunyaev-Zeldovich effect is examined in the volume corresponding to the KBC void, a density deficit is found that is consistent with the galaxy count measurements. Fewer clusters means less hot gas, means a smaller signal per unit volume. The deficit shows up as a statistical underrepresentation of sources within the void's boundaries, compared to the numbers expected from cosmological models. Galaxy counts trace the stellar component of matter, visible stars in galaxies. The Sunyaev-Zeldovich effect traces the hot gas in clusters, a component that is distinct from stars and is particularly concentrated in the most massive objects. The fact that both traces show the same deficit strengthens the case that the void represents a genuine shortfall of all matter, not just an artifact of how galaxy formation happened to proceed in this region. Future cosmic microwave background surveys with higher sensitivity and resolution, including CMB-S4 and the Simons Observatory, will detect Sunyaev-Zeldovich clusters down to lower masses and at greater distances, substantially improving the catalog completeness within the void volume. Combined with improved galaxy surveys, these catalogs will provide much tighter constraints on the void's density profile. It is worth considering how the void affects not just what we see, but how we interpret statistical analyses of the entire observable universe. The observable universe is a sphere roughly 93 billion light-years in diameter. We sit at its center not because we are special, but because the speed of light limits how far we can see. The oldest light we can observe comes from the cosmic microwave background, and it defines the edge of our observational horizon. Within that horizon, we sample only one realization of the universe. We cannot step outside and observe the universe from a different location. We cannot compare our measurements to measurements made from a galaxy outside the KBC Void to check whether our readings are systematically biased. We are stuck with one vantage point, and that vantage point happens to be inside one of the largest underdensities ever observed. This creates a deep epistemological challenge for cosmology. Statistical analyses of cosmic structure assume that we are average observers. They assume the region we observe is a representative sample of the universe as a whole. This assumption underlies the inference of cosmological parameters from the cosmic microwave background, the large-scale structure surveys, and the supernova measurements. If we are not average observers, if our location is systematically unusual, then those parameters may be biased in ways that are difficult to detect and correct for. There is a philosophical tradition in cosmology called the Copernican principle, distinct from but related to the cosmological principle. The Copernican principle states that we are not in a special location. Copernicus displaced Earth from the center of the solar system. Later astronomers displaced the solar system from the center of the galaxy. 20th century cosmology displaced the galaxy from any special cosmic position. The cosmological principle is the generalization of this. No position is preferred, all locations are equivalent on large scales. The KBC Void puts pressure on this deeply held assumption. We may not be at the center of anything, but we may be inside a structure that makes our measurements unrepresentative of the universe as a whole. The distinction matters enormously for precision cosmology. If the void is real and our measurements are biased, then the parameters we call the cosmological constant, the matter density, and the Hubble constant may not accurately describe the universe beyond the void. They describe the universe as seen from inside an unusual bubble. Researchers are developing methods to model and subtract the void's influence from local data. The approach involves measuring the density profile of the void as precisely as possible, running simulations of structure formation in void environments, and using those simulations to predict the expected bias in local measurements. The corrected measurements can then be compared to the early universe constraints to see whether the tension resolves. The challenge is that the modeling requires assumptions about the void's properties that are themselves uncertain. The density deficit might be 10% or 20%. The void's boundary might be sharp or gradual. The shape might be perfectly spherical or subtly elongated. Each of these uncertainties propagates into the correction. Getting the correction wrong could introduce new biases while attempting to remove old ones. This is part of why the upcoming surveys matter so much. Euclid's three-dimensional galaxy map will trace the void's density profile across its full extent with a precision not currently achievable. Dacey's velocity field measurements will map how galaxies move inside and around the void, testing whether the gravitational dynamics match the density profile. Vera Rubin's supernovae will measure the expansion rate at multiple distances throughout and beyond the void. Together, these datasets will provide the observational foundation needed to make the bias correction reliably. One of the more subtle implications of the void concerns what cosmologists call the growth rate of structure. As the universe evolves, density fluctuations grow under gravity. Denser regions grow denser. Empty regions grow emptier. The rate at which this happens depends on the balance between gravity, which promotes growth, and dark energy, which inhibits it by accelerating the expansion. Measuring the growth rate is one of the key tools for testing general relativity on cosmic scales and for constraining dark energy. The standard way to measure the growth rate involves something called redshift space distortions. When you measure the redshift of a galaxy to determine its distance, that redshift includes both the contribution from the expansion of space and the contribution from the galaxy's peculiar velocity, its motion due to local gravitational dynamics. Galaxies falling toward a dense cluster are moving toward you, so they appear to be slightly closer than their true position. Galaxies moving away from a void are moving away from you, so they appear to be slightly farther. This causes galaxy distributions to appear squashed along the line of sight when mapped in redshift space. By measuring the statistical signature of these distortions across many galaxies, cosmologists infer the growth rate. This measurement is sensitive to our local environment. Galaxies inside the KBC Void are experiencing different gravitational dynamics than galaxies in typical regions. The outflow from the void, the infall towards surrounding filaments, and the interaction with the Great Attractor all add velocity components that are specific to our location. Interpreting the redshift space distortion signal without accounting for these local effects could produce a biased growth rate measurement. This matters because the growth rate is one of the clearest tests of whether general relativity is the correct theory of gravity on cosmic scales. Modified gravity theories generally predict different growth rates than general relativity. If the observed growth rate differs from the general relativity prediction, it could signal new physics. But if the apparent deviation is actually caused by systematic effects from the KBC void rather than genuine new physics, the inference would be incorrect. Distinguishing between these possibilities requires understanding the void's influence on local velocity fields in quantitative detail. The peculiar velocity surveys that are becoming possible with new instruments will help. By measuring the velocities of thousands of galaxies across the void and comparing them to predictions based on the observed density field, researchers can test whether the relationship between density and velocity is what general relativity predicts. Any excess or deficit in the velocity field relative to density predictions would indicate modified gravity. This is a direct, local test of gravitational physics in a low-density environment. Consider also what the void tells us about the early universe. The void's existence today is the outcome of a density fluctuation that was seeded during cosmic inflation more than 13 billion years ago. The fact that such a large, deep underdensity exists places constraints on what the inflationary density fluctuations looked like. The initial density contrast at the scale corresponding to the KBC void must have been sufficient to produce the observed void after 13 billion years of gravitational evolution. In the standard inflationary model, the amplitude of density fluctuations at a given scale is characterized by a quantity called the primordial power spectrum. The power spectrum describes how much density contrast exists at each scale. Standard slow-roll inflation predicts a nearly scale-invariant spectrum, meaning approximately equal power at all scales. This prediction agrees remarkably well with cosmic microwave background observations across a wide range of scales. But the scales corresponding to supervoids like the KBC void are among the largest accessible scales, close to or beyond the scale at which the cosmic microwave background provides precise constraints. If there is a feature in the primordial power spectrum at these large scales, perhaps extra power that standard slow-roll inflation would not predict, it could explain why supervoids are more common than standard simulations suggest. Detecting such a feature requires mapping the universe at very large scales, which is precisely what Euclid and its contemporaries are designed to do. The connection between the KBC void and inflation runs deeper still. Some inflationary models predict not just a power spectrum, but specific non-Gaussian features in the density field, patterns of density correlation across space that deviate from what a purely random Gaussian distribution would produce. Large supervoids are particularly sensitive to these non-Gaussian features because they represent extreme events in the tail of the density distribution. A slight enhancement in the non-Gaussianity of the primordial fluctuations could make extreme voids more likely, potentially resolving the statistical tension between the KBC void's existence and LCDM predictions. Measuring primordial non-Gaussianity requires galaxy surveys that span enormous volumes. The signal is subtle and requires averaging over billions of galaxies to extract it from the noise. Daisy and Euclid will make the first serious measurements of primordial non-Gaussianity through the large-scale distribution of galaxies. If non-Gaussianity is detected at the level suggested by some modified inflationary models, it would simultaneously explain the KBC void's existence and refine our picture of what happened in the first fraction of a second after the Big Bang. There is a dimension to the void story that is rarely discussed, but is scientifically important: the fate of the data itself. Astronomical knowledge is cumulative. The discoveries made by the upcoming generation of surveys will be recorded in databases that will be publicly accessible to researchers worldwide. The galaxy positions mapped by Euclid, the velocity fields measured by Daisy, the supernova distances catalogued by Vera Rubin, the gravitational wave events detected by LIGO and its successors, all of these will contribute to an ever more complete picture of our cosmic neighborhood. Within a decade, we will have a three-dimensional map of the galaxy distribution, extending to distances of several billion light-years, with a completeness and precision that would have seemed almost impossibly ambitious a generation ago. That map will answer, definitively, whether the KBC Void's density deficit is 10% or 20%. It will reveal whether similar structures exist at greater distances and how common they are. It will trace the velocity field within the void to test whether the expected gravitational outflow is present. It will determine whether the void's edges are sharp or diffuse, symmetric or irregular. Each of these measurements will feed back into cosmological models. Simulations will be run with the updated parameters. Theoretical predictions will be refined. The standard model will either accommodate the new data with minor adjustments or face the need for more fundamental revision. The scientific process is not a single eureka moment. It is a continuous narrowing of uncertainty through the accumulation of evidence. The KBC Void is a perfect example of this process in action. A straightforward observation, counting galaxies within a billion light-years and finding 20% fewer than expected, cascades into questions about the expansion rate of the universe, the age of the cosmos, the nature of dark energy, the validity of the cosmological principle, the behavior of gravity on large scales, and the reliability of every precision measurement in modern cosmology. Each of these questions is individually significant. The void connects them into a single coherent puzzle. What makes the void particularly intellectually interesting is that it is simultaneously a local structure and a window onto fundamental physics. It is local in the sense that it surrounds us and affects every measurement we make from our position. It is a window onto fundamental physics in the sense that its very existence, its scale, its depth, and its rarity place constraints on theories of gravity, inflation, dark energy, and structure formation. Studying it requires precision measurements of our immediate cosmic neighborhood and simultaneously pushes the frontier of theoretical physics. The scientists working on these questions are not looking for dramatic revolutions, though revolutions may come. They are following the evidence methodically, improving measurements, reducing uncertainties, and testing theoretical predictions against observations. The void hypothesis for the Hubble tension makes specific, testable predictions. Those predictions will be tested. The outcome will either confirm the hypothesis, refine it, or rule it out. In any of those outcomes, our understanding of the universe will advance. We are in the middle of this story. The instruments are being built, the surveys are beginning, the data is accumulating, the analysis pipelines are being developed and validated within 10 years. Many of the questions now open about the KBC Void will have definitive answers. Whether the void resolves the Hubble tension completely or only partially, whether it requires new physics or can be accommodated within the standard model, whether it represents a genuine challenge to the cosmological principle or falls just within its expected range. These are empirical questions, and the empirical tools to answer them are now in hand. What we know with certainty right now is this. We are inside a bubble of space roughly 2 billion light-years across where matter is measurably scarce. That structure is affecting our measurements of cosmic expansion. It may be introducing systematic biases into parameters we have long treated as known, and it challenges, at minimum, our intuition that we occupy an average, unremarkable position in the universe. The void is real, its effects are real. The questions it raises are among the deepest in contemporary science, and the answers, when they come, will tell us not just about the void itself, but about the nature of space, the behavior of gravity, the properties of dark energy, and the physical laws that govern the universe's first moments. Not bad for a region of space defined by what it does not contain. To fully appreciate why the KBC Void matters, it helps to understand just how central the Hubble constant is to every other measurement in cosmology. The Hubble constant is not just a number about how fast the universe expands. It sets the scale of the universe. It determines distances. It sets the age. Every time an astronomer reports the distance to a galaxy, a quasar, a gravitational wave source, or a gamma-ray burst, that distance is calculated using an assumed value of the Hubble constant. If the Hubble constant is wrong by 9%, then every distance in the universe that depends on it is wrong by a corresponding amount. This matters for measurements of the sizes of structures, the sizes of galaxy clusters, the lengths of cosmic filaments, the diameters of supervoids like the KBC Void itself. It matters for measurements of the ages of objects, the age of distant quasars, the cosmic epoch at which particular galaxy populations formed, the time when the first stars ignited. It matters for the inferred properties of dark energy, because dark energy's influence on expansion history is inferred from how distances change over cosmic time, and those distances are calibrated using the Hubble constant. A systematic error in the Hubble constant is not just an error in one number. It is a systematic error that propagates through the entire edifice of modern cosmology. This is why the Hubble tension is taken so seriously. The two independent measurements, 67 from the early universe and 73 from the local distance ladder, have been checked, rechecked, and verified independently by dozens of teams using different methods. The discrepancy does not go away, it persists. It has grown more statistically significant as measurements have improved. The void hypothesis is one of the most physically motivated explanations for why the local measurement might be systematically elevated. It does not require exotic new physics. It does not require abandoning general relativity. It requires only that we account for the fact that we are not located in an average region of the universe. The mass distribution around us is unusual. The gravitational dynamics of our neighborhood are influenced by that unusual mass distribution. Our measurements of expansion reflect that influence. The most compelling feature of this explanation is that it is quantitatively consistent. The size of the KBC Void, its measured density deficit, and the expected gravitational boost from the surrounding shell of dense structure all combine to produce a predicted elevation in the locally measured Hubble constant that matches the observed discrepancy. This is not a vague hand-waving explanation. It is a specific numerical prediction that happens to match a specific numerical discrepancy. That level of quantitative consistency is unusual and important. To understand the scale of the void in more intuitive terms, consider the following. The distance from Earth to the nearest star outside the solar system, Proxima Centauri, is about 4 light-years. The distance from one edge of the KBC Void to the other is about 2 billion light-years. That is 500 million times the distance to our nearest stellar neighbor. If you could travel at the speed of light, crossing the void from one side to the other would take 2 billion years. The universe itself is only 13.8 billion years old. The void spans more than 14% of the age of the universe in travel time. Put another way, the KBC Void is so large that light from a galaxy on one side of the void that departed before complex life appeared on Earth has not yet reached the other side. It is not an empty patch between two galaxy clusters. It is a continent-sized region of the cosmos, and we are inside it. The history of observational confirmation of the void is itself interesting. The initial 2013 paper by Keenan, Barger, and Cowie used a photometric redshift survey of galaxies to count how many objects existed within various distance shells. Photometric redshifts are estimated from the colors of galaxies rather than their spectra and are faster to obtain but less precise than spectroscopic measurements. This introduced some uncertainty into the original results. Subsequent work using spectroscopic redshift surveys, which measure galaxy distances from their actual spectra and are far more precise, confirmed the basic finding. The surveys used included the Sloan Digital Sky Survey, the 2-degree field galaxy redshift survey, and several others. Each approached the problem from a different direction with different instruments and different systematic errors, yet all found evidence for a large underdensity in our local region. Independent confirmation came from weak gravitational lensing. Weak lensing occurs when the gravity of intervening matter slightly distorts the shapes of background galaxies. By statistically analyzing the distortions in the shapes of millions of galaxies, cosmologists can infer the distribution of matter between those galaxies and us. The matter distribution inferred from weak lensing in our local region is consistent with the density deficit seen in galaxy counts, providing confirmation from a completely different physical process. Peculiar velocity surveys provide yet another independent line of evidence. If we are inside a void surrounded by a denser shell, the galaxies around us should show a specific velocity pattern. Galaxies near the void's edge should be moving outward, away from the void's center. due to the gravitational imbalance. Galaxies just beyond the shell should be moving inward, toward the shell, for the same reason. Surveys measuring peculiar velocities of nearby galaxies have found patterns broadly consistent with this expectation. The convergence of evidence from galaxy counts, spectroscopic surveys, weak gravitational lensing, peculiar velocity fields, and Sun-Eves-Eldovich cluster counts all pointing to the same basic picture gives researchers substantial confidence that the void is real. No single method is definitive. The systematic errors associated with each technique are different. But when independent methods with different systematics all find the same thing, the case for the reality of the observed structure is strengthened. At the same time, the uncertainties in the void's properties remain large enough to matter for the questions the void raises. A 10% density deficit is much less statistically extreme in simulations than a 20% deficit. A void that is slightly smaller and shallower than the most generous estimates is less threatening to the standard model. Nailing down the exact magnitude of the deficit, the precise extent of the void, and the sharpness of its boundary are therefore critical scientific priorities. These numbers determine whether the void is a problem for standard cosmology or merely a feature within its expected range. The way voids are identified and characterized has itself been an active area of methodological development. Finding voids in galaxy surveys requires defining what a void is, which turns out to be less straightforward than it sounds. Is a void defined as a region with fewer than average galaxies? By how much less than average? Over what smoothing scale? What happens when two overlapping underdense regions are present? Different algorithms for finding voids in surveys give different catalogs with different statistical properties. For the KBC Void specifically, its large scale means that systematic effects in surveys, like incomplete sky coverage or variations in survey depth across different regions, become particularly important. A genuine underdensity spread uniformly across the sky is hard to distinguish from a systematic effect that uniformly reduces the observed galaxy count in all directions. The checks against multiple independent surveys with different systematic profiles were critical for establishing that the deficit is real rather than artifactual. As galaxy surveys extend to greater distances and higher completeness, the environment just beyond the KBC Void's boundary will be mapped with increasing detail. This will allow direct comparison of the density within the void to the density in surrounding regions, providing a direct measurement of the density contrast that determines the void's gravitational influence. The current estimates range from 10 to 20%. Future surveys will pin this number down to a few percent precision, dramatically improving the reliability of the predicted Hubble constant boost. The broader context here is one of cosmology entering a new era of precision. In the 1990s, cosmological parameters were uncertain by factors of 2 or more. The Hubble constant was debated between values of 50 and 100 kilometers per second per megaparsec. By the 2010s, precision measurements from the Planck satellite, the Hubble Space Telescope, and large galaxy surveys had reduced uncertainties to a few percent. The Hubble tension became visible only because measurements became precise enough to make it significant. The tension is, in a sense, a consequence of success. Cosmology became precise enough to detect a 9% discrepancy that would have been invisible a generation earlier. The next generation of surveys will push precision further still. Euclid aims to measure the Hubble constant to sub-percent precision. Vera Rubin will measure it with comparable precision from supernovae alone. Dacey will constrain it through baryon acoustic oscillations. Gravitational wave detectors will measure it directly from standard sirens. If the void is the dominant cause of the tension, and if the void's properties are correctly understood, then as these measurements extend to greater distances outside the void, the locally and globally measured values should converge. The tension should shrink. If the tension does not shrink, if the discrepancy persists even after the void's influence has been accounted for, then something else is at work. Perhaps dark energy is not a cosmological constant. Perhaps there are additional relativistic degrees of freedom in the early universe that affect the expansion rate. Perhaps the distance ladder has a systematic calibration error at some step. Perhaps general relativity needs modification. Each of these possibilities is already being investigated, and the new datasets will constrain them all simultaneously. The richness of the scientific landscape here is part of what makes the coming decade so exciting for cosmology. The KBC Void is one thread in a larger tapestry of observations and theoretical ideas that are all converging on the same set of questions. What is the universe made of? How fast is it expanding? Why? How did structure form? How will it evolve? These questions are not new. But the tools to answer them are now more powerful than they have ever been, and the constraints they are beginning to impose are tight enough to reveal cracks in our understanding. The void we inhabit is both a specific local feature and a symbol of the broader challenge facing modern cosmology, the challenge of understanding the universe from a single, potentially biased, vantage point. We cannot move. We cannot observe from outside. We must infer the properties of the entire cosmos from measurements made inside one small region of it, a region that turns out to be unusually empty. The best science acknowledges this challenge explicitly and works to quantify and correct for it. The growing recognition that our location in the KBC Void may be influencing our measurements is an example of cosmology doing exactly that, being rigorous, self-critical, and committed to understanding not just what the data says, but what the data means given the conditions under which it was collected. The void does not make our measurements useless, it makes them more complex. The complexity is manageable, given enough data and enough theoretical understanding. The data is coming, the understanding is developing. In 10 years, the picture will be far clearer than it is today. And whatever that clearer picture shows, whether it vindicates the standard model, demands modifications, or reveals something genuinely unexpected, it will represent a genuine advance in humanity's understanding of the cosmos. We are inside a void 2 billion light-years across. The measurements we make are colored by that fact, and the work of understanding what that means for our knowledge of the universe is among the most fascinating scientific investigations underway anywhere in the world. There is another dimension to the KBC Void story that is easy to overlook when focusing on the Hubble tension. The void is also a unique laboratory for understanding galaxy formation at the extremes of the density distribution. Most of what we know about how galaxies form and evolve comes from observations of galaxies in typical or high-density environments. Clusters, filaments, groups, these are where most of the mass is, where most of the galaxies are, and where most observations have been concentrated. The physics of galaxy formation in those environments is reasonably well understood in its broad strokes, even if many details remain unclear. Voids represent the opposite extreme. In void environments, the density of matter is low, the merger rate is low, the gas accretion rate is low, and the external gravitational influence from neighboring structures is minimal. Galaxies in voids are evolving in as close to isolation as the universe allows. They provide a clean environment in which to test theoretical predictions about galaxy formation without the complicating influence of dense surroundings. The galaxies that do form inside the KBC Void are particularly interesting objects. They are predominantly blue, disk-dominated galaxies, still actively forming stars from their gas reservoirs, relatively undisturbed by mergers or tidal forces. Their dark matter halos are more spherical and less massive than the halos of typical cluster galaxies. Their central black holes are less massive and less active. They are, in a sense, simpler objects than the massive, complex galaxies found in dense regions. Studying these void galaxies offers tests of several poorly understood processes in galaxy formation. How does gas accrete onto galaxies in the absence of filamentary feeding? How do supernovae and stellar feedback regulate star formation when there is no external ram pressure to remove gas? How do black holes grow when there are no mergers to funnel gas into galactic nuclei? What is the lower mass limit for galaxy formation in the low-density void environment, where the intergalactic gas is more diffuse and harder to accrete? These questions can be answered observationally by cataloging and characterizing the galaxy population within the KBC Void and comparing it to theoretical predictions. Current surveys have identified the broad outlines of the void galaxy population. Future surveys with deeper sensitivity will find galaxies down to lower masses and luminosities, probing the faint end of the luminosity function in void environments. This faint end is where many of the disagreements between theory and observation have been concentrated. The standard model predicts many more faint dwarf galaxies than are observed. This missing satellites problem is one of the long-standing puzzles of cosmology. In void environments, where the suppression of galaxy formation might be strongest, the missing satellites problem may be even more acute. Measuring how the luminosity function of galaxies changes from dense to void environments will constrain the processes responsible for the missing satellites. The intergalactic medium inside voids is also a distinct environment with its own observable properties. The warm-hot intergalactic medium, the gas that fills the space between galaxies and is not gravitationally bound to any single structure, is less dense and cooler in voids than in filaments. This affects the way that ultraviolet light from background quasars is absorbed as it passes through void gas, a phenomenon studied through the Lyman alpha forest in quasar spectra. The Lyman alpha forest is the series of absorption lines seen in quasar spectra produced by hydrogen clouds at various distances along the line of sight. By analyzing the statistical properties of these absorption features, cosmologists can map the distribution of hydrogen gas across large volumes of space. The density of the gas in void regions versus filament regions is directly measurable from this technique. Comparing those measurements to theoretical predictions of how gas distributes in low-density versus high-density environments provides another test of structure formation models. Future quasar surveys will dramatically increase the number of lines of sight available for Lyman alpha forest analysis within the KBC Void's volume. By mapping the void's gas distribution in 3 dimensions using the forest technique, researchers will be able to trace the matter distribution at scales below what galaxy counts can reach, since the gas traces the overall matter distribution, even in regions too sparse to form visible galaxies. This will fill in the detailed picture of the void's interior that galaxy counts alone cannot provide. It is also worth noting that the KBC Void is not unique in the sense that there are no other supervoids. The universe contains other large underdensities, though none as well studied from the inside. The Boots Void, discovered in 1981, is a nearly spherical void about 330 million light-years across with very few galaxies inside it. The Eridanus supervoid, discovered in 2015 as a potential explanation for the large cold spot in the cosmic microwave background, spans roughly 1 billion light-years. If the Eridanus supervoid is responsible for the cold spot, it would be through the same integrated Sachs-Wolfe mechanism, photons losing energy as they pass through the low-density region. The KBC Void is larger than either of these, and crucially, we are inside it. Being inside a void rather than observing it from outside changes everything about how it affects our observations. A void we can observe from outside simply makes measurements through it more complicated. A void we are inside of systematically biases every measurement we make in every direction. Comparing the KBC Void to external supervoids is scientifically valuable precisely because it allows testing whether the same physics operates in both cases. If the integrated Sachs-Wolfe signal from the Eridanus supervoid matches predictions, and if the velocity field around the Boots Void follows the expected outflow pattern, those observations strengthen the case that the KBC Void's effects on our local measurements are also real and predictable rather than exceptional. Network of upcoming observatories will observe all of these structures simultaneously. Euclid and Vera Rubin will map not just our local void, but supervoids throughout the observable universe. The statistical comparison of many voids at different distances and sizes will establish whether their properties follow the expected distribution, how their galaxy populations differ from typical environments, and how their expansion rates compare to predictions from different dark energy models. There is a concept in philosophy of science called the underdetermination of theory by evidence, the idea that any given set of observations can in principle be explained by more than one theory. In cosmology, this is a constant challenge. The data we have can often be fit by the standard model with one set of parameters, or by a modified theory with different parameters. Without additional discriminating observations, it is impossible to determine which explanation is correct. The KBC Void is a potential discriminator. It makes specific quantitative predictions that differ from those of a universe with no such void. If the predictions are confirmed, the void explanation is strengthened. If they are refuted, the void hypothesis is weakened or ruled out. The measurements needed to test those predictions are being made. The data is accumulating. The discrimination is becoming possible. This is the scientific method working as it should, observations suggesting a hypothesis, the hypothesis making specific predictions, those predictions being tested, and the outcome determining the hypothesis's fate. The void hypothesis is not certain. It may be wrong. It may be only partially correct, with the void explaining part of the Hubble tension while other factors explain the rest. The evidence will decide. What is certain is that the KBC void exists, that it is real and measurable, and that it is large enough to affect our measurements of the universe. That much is established. What remains uncertain is the quantitative magnitude of its effects, the exact density deficit, the precise extent, the strength of the resulting Hubble constant bias, and whether those effects fully explain the observed tension or leave room for additional new physics. The scientific community is not paralyzed by this uncertainty. It is energized by it. The prospect of resolving one of the most significant tensions in modern physics, of determining whether the standard cosmological model needs modification, of mapping the largest local structure in the observable universe, of testing gravity in the most extreme low-density environment accessible to observation. These are compelling scientific goals. The instruments being built are designed to address them. The careers being built around these questions reflect how seriously the scientific community takes them. We stand inside a void 2 billion light-years across, taking measurements of a universe we can only observe from this one unusual vantage point. The measurements we make are real. The structures we observe are real. But interpreting what they tell us about the universe as a whole requires understanding the conditions under which the measurements were made. The KBC void is those conditions. Understanding it is not a distraction from cosmology. It is cosmology. The next decade will answer many of the open questions. The answers, whatever they are, will advance our understanding of where we are, what surrounds us, and what the universe beyond our unusual cosmic neighborhood is actually like. The void is empty of matter. It is not empty of scientific meaning. One further layer to this story deserves attention: the psychological challenge the void presents to cosmologists themselves. For decades, the standard cosmological model has been refined with increasing precision. The Planck satellite's measurements of the cosmic microwave background in the 2010s produced cosmological parameters with sub-percent uncertainties. The model seemed mature. The broad questions seemed answered. Cosmologists spoke of moving from a period of discovery to a period of precision. The Hubble tension disrupted that narrative, and the KBC void complicates it further. The possibility that every precision measurement made over the last generation of cosmology might be systematically biased by our location inside an underdense bubble is not a comfortable one. It means that the confidence intervals on those measurements, expressed as precise percentages, may not reflect the true uncertainty about the properties of the universe as a whole. Scientists are trained to quantify uncertainty. Error bars on measurements represent known sources of uncertainty: statistical noise, systematic calibration errors, model-dependent assumptions. But there is a category of uncertainty that error bars often do not include: the uncertainty arising from not knowing whether the conditions under which the measurement was made are representative of the system being studied. The KBC void is a source of this harder-to-quantify uncertainty. When the cosmic microwave background is used to infer the global Hubble constant, the analysis assumes that the universe is homogeneous. The void introduces a deviation from homogeneity, but the CMB measurement is made from inside the void too, since the CMB light passes through the void before reaching our telescopes. Does the void affect the CMB measurement in the same way it affects the local distance ladder measurement, or differently? The answer is not obvious, and working it out requires careful modeling. The integrated Sachs-Wolf effect mentioned earlier suggests that photons passing through the void do experience a change in energy. The effect is small at the scale of the KBC void, but it is not zero. If the temperature of the cosmic microwave background is slightly affected by the void in a direction-dependent way, that could in principle introduce small systematic shifts in the inferred CMB temperature spectrum. Those shifts are small and may be below the precision of current measurements, but they represent a source of uncertainty that must be accounted for as precision improves. These second-order effects, the effects of the void on the void's own observational signature, are at the frontier of what theoretical cosmologists are now working out. The calculations are complex. They require perturbation theory applied to a non-uniform background, which is technically demanding. The results will guide the analysis of future datasets and determine how much of the measured Hubble tension can confidently be attributed to the void versus other causes. There is also the question of how the void affects measurements of the matter-power spectrum, the statistical description of how matter is distributed at different scales throughout the universe. The matter-power spectrum is one of the most information-rich observables in cosmology. Its amplitude at small scales encodes information about the total amount of matter in the universe. Its shape at large scales encodes information about the nature of dark matter and the initial conditions from inflation. Tensions have emerged in recent years between the amplitude inferred from the cosmic microwave background and that inferred from weak gravitational lensing surveys, a discrepancy that may also be influenced by our local environment. If we are inside a void, the galaxy count in our vicinity is lower than the cosmic average. Weak lensing measurements sensitive to the matter distribution within and near the void would reflect this lower density. When those measurements are used to infer a global amplitude for matter fluctuations, they would produce a value lower than the true global average. This could explain part of the observed tension between CMB-based and lensing-based matter amplitude measurements, known as the sigma-8 tension, which has been sitting alongside the Hubble tension as another unresolved discrepancy in modern cosmology. Both tensions, Hubble and sigma-8, may therefore have a common origin in our position inside the KBC void. This would be a satisfying resolution, a single physical fact about our location, explaining two apparently independent discrepancies in the data. Testing this idea requires modeling how the void affects both expansion rate measurements and matter amplitude measurements simultaneously, and checking whether the predicted biases are large enough to explain both tensions without invoking additional new physics. Several research groups are actively pursuing this analysis. The question of whether the sigma-8 tension can be explained by the void is particularly interesting because the lensing measurements that constrain sigma-8 span a range of scales and distances. If the void influence declines at large distances, as expected once measurements extend beyond the void's boundary, the inferred sigma-8 should increase toward the CMB predicted value. Measuring sigma-8 as a function of redshift, or equivalently distance, is therefore another test of the void hypothesis. The upcoming surveys, particularly Euclid with its galaxy shape measurements extending over billions of light years, are well suited to this test. Each of these threads, the Hubble tension, the sigma-8 tension, the integrated Sachs-Wolf signal, the peculiar velocity field, the galaxy population statistics, the modified gravity tests, the primordial non-Gaussianity constraints, weaves back into the same central feature: the enormous, real, measurable underdensity that surrounds us in every direction and extends for 2 billion light years. The KBC void is not one problem in cosmology. It is a hub connecting many problems. And the work of understanding it, of measuring it precisely, of modeling its effects on our observations, of testing whether it can explain the discrepancies that have accumulated in the precision cosmology era, is some of the most important work in the field today. In the history of science, there have been moments when seemingly separate anomalies turned out to have a single underlying cause. The discovery that the precession of Mercury's orbit, the bending of light around the Sun, and the gravitational redshift of clocks were all consequences of general relativity replaced three puzzles with one elegant theory. The void hypothesis for the Hubble tension and related discrepancies has the character of such a potential unification, explaining multiple apparently separate anomalies through a single, physically well-motivated, observationally confirmed structure. Whether it will succeed as a complete explanation remains to be seen. The evidence so far is suggestive but not conclusive. The upcoming decade will make it conclusive. That is what is so remarkable about the moment we are in. The questions are well posed, the measurements are feasible, the instruments are being built, the answers are within reach. We are inside the KBC void. That fact is not going to change. What will change over the next 10 years is how well we understand what that fact means for our knowledge of the universe. And the scientific community, with its new telescopes and new techniques and new generations of researchers, is determined to find out. Let us return to one more underappreciated aspect of the KBC void, how it reshapes our understanding of our own position in the history of the universe. We exist at a specific moment in cosmic time. The universe is approximately 13.8 billion years old. The void we inhabit has been growing, emptying, and expanding throughout that entire history. The density deficit we observe today is the product of 13 billion years of gravitational dynamics, beginning from a small initial fluctuation in the density field left by inflation. In the early universe, the region that would become the KBC Void was not yet empty. It was only fractionally less dense than surrounding regions, by perhaps 1 part in 100,000, the same scale as the quantum fluctuations inflated to cosmic sizes during the inflationary epoch. Gravity worked on that tiny seed deficit over billions of years, slowly draining matter from the underdense region into the surrounding filaments, progressively deepening and widening the void. By the time the first stars formed, roughly a few 100 million years after the Big Bang, the void was beginning to take shape. By the time the solar system formed 4.5 billion years ago, the void was well developed. By now, it has grown to its present enormous extent. The Milky Way has spent its entire history inside an increasingly empty bubble of space, growing up in a low-density environment, shaped by forces that pull it toward the great attractor, while the void's expansion pushes its contents outward. This historical perspective changes the way you think about the Milky Way's formation and evolution. Our galaxy did not form in a typical environment. It formed inside a supervoid, in a region where the density was below the cosmic average, where neighbors were fewer and farther apart, where the intergalactic medium was less enriched and less compressed. The conditions that shaped the Milky Way's size, structure, and star formation history were influenced by the void environment in ways that are only beginning to be systematically studied. The solar system formed from material that had been processed through several generations of stars inside the Milky Way. The composition of that material, the abundances of carbon, oxygen, iron, and the other elements that make up planets and life, reflects the star formation history of the galaxy. And that history was shaped by the galaxy's environment inside the void. We are, in a very real sense, the product of the void. Our existence is connected to the unusual density environment that has surrounded our galaxy throughout its history. This does not imply anything mystical or anthropic in the strong sense. It is simply a recognition that conditions matter for outcomes. The conditions inside the KBC Void produced a galaxy like the Milky Way, orbiting a star like the Sun, at a time when the cosmos was old enough to have enriched the interstellar medium with enough heavy elements for rocky planets and complex chemistry. Those conditions were shaped by the void. The void was shaped by inflation. Inflation was shaped by physics we are still working to understand. The chain of causation stretches back to the earliest moments of time. Understanding where we are in the cosmos, not just the address of Earth in the solar system, in the galaxy, in the local group in Laniakea, but the full context of the density environment, the void, the surrounding shell, the broader cosmic structure beyond, is part of what it means to know our place in the universe. The KBC Void is part of that address. It is not a footnote. It is a defining feature. The measurements being made right now, the galaxy surveys mapping our cosmic neighborhood, the gravitational wave detectors listening for standard sirens, the microwave background experiments mapping the Sachs-Wolf signal, the quasar spectroscopy tracing the intergalactic gas, all of these are contributions to a more complete picture of where we are and what that means. They are the work of thousands of scientists across dozens of countries, building instruments, developing algorithms, writing software. Analyzing data, writing papers, debating interpretations, and slowly converging on the truth. The truth, when it comes, will be about a void, about emptiness, about the region of space characterized by what it lacks. And yet understanding that emptiness turns out to require some of the most sophisticated science ever done, touching the deepest questions about the nature of gravity, the properties of dark energy, the history of inflation, and the reliability of our knowledge of the cosmos. The void is empty of matter. It overflows with scientific content. Science rarely arrives at clean conclusions. More often, discoveries open onto further questions, and the apparent resolution of one problem reveals others lurking underneath. The KBC Void is a perfect example of this process. What began as a straightforward observational survey, counting galaxies and finding fewer than expected, has grown into one of the most consequential and interconnected puzzles in contemporary cosmology. The void is real, its effects are measurable, and the work of understanding it is among the most fascinating scientific investigations underway anywhere in the world today. That is not dramatic phrasing. It is simply true. We are inside a bubble 2 billion light-years wide. Everything we know about the universe, we learned from here.